Yes, and share screen, whiteboard. Right, so today's lecture, I think it's 22. I lost a bit the count, but I believe we are number 22. So it will be mostly about molecular motors, which I briefly introduced before. So this is lecture 22, which will be molecular motors. Which I will give here a brief introduction about them, not the most complicated model, but just an introduction about these systems. So just as a sketch, I will begin with a simple sketch on what is a molecular motor. Just as a reference, let me just say that I will follow a paper here instead of a book. Mostly the paper that I will follow is called the following. It's a review paper. The title is the following: Modeling Molecular Motors. Molecular motors. These are the authors. Pro. The journal is a Review of Modern Physics. Modern Physics. And the year is 1997. So when there's a review article, it means there has been a lot of research previous to this year, but it doesn't mean all the research on this topic has been finished. So still, molecular motors is a very active area of research, which involves biologists and physicists and chemists and scientists of different disciplines. So this review is very nice. I highly recommend you to read it, and I will go through some of the key concepts that are discussed here. So in this review, they discuss motors which move along filaments, moving in filaments, in the same way in which the filaments function as railway tracks or freeways. So you have to think like the filament is the track, is the railway or the freeway, and the motors is like the car. Okay, the structure of the motors can be different. It can have two heads, one head, and so on. And the filaments, their main characteristic is that they will be periodic. Filaments are periodic. They have a periodic structure. They are fairly rigid, and they have a period of they are rigid mostly, and they have a period of the order of 10 nanometers, okay, the order of 10 nanometers. You can think about the microtubule, for example, which we had this tube I was discussing in the previous lecture, and the tube had monomers. So this tube can be seen as a periodic track in which the distance between each of the monomers is 10 nanometers. This can be a microtubule. And on top of that, there are machines that are moving in a given direction, and they are transporting cargo. The lecture of today is about these machines, how they move, and how we can generate motion in a fluctuating environment. So as a sketch, as is given in this paper, we have this type of sketch in which we have a track. Okay, maybe this is not the best drawing. Let me start from here. So there is a track, which is the filament, like this. And the filament has structures. It has monomers. The filament is a polymer that we will consider is not growing. We consider it's fixed, and we will think that there is a machine moving on this track. Okay. Okay, this is a very bad drawing, but just to give you an idea, this is a periodic structure, the filament. This is a polar filament. And there is a machine, which is the motor, that is moving on top of this. So the motor, I will draw it, I don't know, for example, in brown here. The motor will be sitting at some point here. Obviously, this is a simplification. This is the motor. Molecular motor is the size of nanometers. And this motor, it's pulling a cargo, so it can move other molecules, such as vesicles. So it is attached to a cargo that is behind the motor. It can be much bigger than the motor itself, even. This is the cargo. It's like a load. And the motor, because of the fact that it's attached to a cargo, it is subject to an external force. So this cargo is pulling the motor. And we say this is pulling with, put here a drawing, which is the external force, F external. Okay. The cargo is pulling the motor, but still the motor can move and has speed. So the motor, it's yet can move against external forces. And this we will say this is the velocity of the motor. So yet there is an external force. The motor can oppose external force and move in this direction in the filament. Why the motor is able to do this is the key question I will try to discuss in this lecture. Okay, the motor obviously is fueled. So like the car of an engine, you use fuel, you burn fuel every time you turn on the engine of a car. This can be seen like a car which has a very specific engine, which is chemical reactions. So this motor is powered by chemical reactions. In particular, it can use, for example, ATP. It can bind ATP, adenosine triphosphate, can bind to the motor, so ATP can bind to the motor, and then be hydrolyzed into ADP plus P. Okay, ADP plus P. So this is ATP hydrolysis, and as I told you in the previous lectures, this gives you energy. And this, we say, it will happen at a given rate. So we will say that this process is happening at a rate R. Okay. So there are two key concepts here. So one is R, and the other is V. So R is the ATP consumption rate. ATP consumption rate. Of course, if R is negative, it's like we have the opposite direction. But we will say R is positive. So this is ATP consumption rate. It has units of, it can have units of seconds minus 1, for example, how many ATPs is consumed per second. And V will be the net motor velocity. Okay. I will first discuss this type of machines on averages by looking at what is the average velocity, in terms of the other parameters. And then I will introduce stochastic models, which we can use for understanding the fluctuations of the motor. Okay, so this is more or less the picture that you have to think about. And of course, if we think about models, so we can do models in which we have the mean velocity in terms of the other parameters, or we can have stochastic models. Stochastic models can be of different types. We could do, so there will be mean field models, which I will discuss first. Models for averages. And there will be also later stochastic models of different types. Okay. To describe molecular motors, you can use both discrete and continuous models. So one can use, for instance, this type of Markov jump models in which each of these state is so it's the center of mass position of the motor. It can be closer to this state than this one, and so on. Every time it moves, the smallest distance is not with this monomer, but with the next one. This is, in a way, you can think about it like a jump process between different states. This is one approach that people use, which are Markov jump process. But you can also think that the center of mass of the motor is a continuous variable. So then the motor is moving like in a periodic potential, like this could be, no? So this is a particle that moves in a periodic potential. So this will be like a Markov jump, as I said. Jump, which many people use. I have also used in my research this type of models. But today I will focus more in this type of models, which are Fokker-Planck or Langevin type. Okay, this is X is continuous. Fokker-Planck or Langevin descriptions. Okay. So the physics insight behind this motion is that molecular motors are microscopic objects that move along one-dimensional periodic structures. Okay. And the key point here is, the key question is how to generate these motions, how to rectify, this concept is rectify fluctuations at small scales. So this was a question that has attracted the attention of many physicists. And the key point is, you have a particle in a potential. How can you use the fluctuations such that the particle has a net velocity? So if you have a particle in one potential doing a diffusion, there won't be a current because this will reach equilibrium. It won't have a net velocity in any direction. So physicists have thought about this problem in different ways. And one option is, for example, introduced in the so-called Buttiker-Landauer ratchet. These are two different papers by two people. One is Buttiker in the 1988, and the other is Landauer. Landauer is very important in information theory as well. 1988, Buttiker-Landauer ratchet. This is a model which is continuous, which generates motion. Ratchet, sorry, this is a T, which is as follows. So you have a potential, which is periodic, something like this. So for example, a sine, this is V of x. And you say, okay, if I have a particle diffusing here, in general, it will jump to the right and to the left with equal probability. So we won't have a current like in a molecular motor. So in principle, this model is not valid. Of course, if you put a force everywhere, it will be like a tilted potential, and this will have motion. But that's very obvious, and that's not the case always of molecular motors. So this is something that is not, you cannot have a constant force everywhere. This will take infinite energy. This is not the reality. What these people thought about was the following, was about a particle in a periodic potential, but in which the temperature of the bath, because this is in a thermal bath, the temperature of the bath is not homogeneous, but it is in an inhomogeneous temperature environment. So it will be a temperature that will do, for example, it could, I mean, there are many ways to do it, but one way would be, for instance, to have a high temperature. Sorry, oh. This is not nice. Now I don't know how to go back, undo. Yes, okay. So one way would be to have something like this, in which we have a temperature that is, for example, high here, is low here, is high here, is low here. It has a dephasing with the potential. Okay. When you have a space-dependent temperature, T of x, you can generate, with this type of models, you can generate a current. This is not an obvious effect, but this is a possibility that one can yield a net current in one direction. So this is one possibility. This could be also, instead of T of x, it could be a space-dependent diffusion, D of x. When you have this type of models, and D and V are periodic, but the period, they are not matching on top of each other, there is a difference of phase, this generates transport. However, what you need here are temperature fluctuations. So you need to hold, for example, in this structure, an inhomogeneous temperature profile. However, this is very, very difficult to have in a molecular motor. These are often in a thermal bath at a fixed temperature T. So this is a good idea, this one, but it's not realistic because fluctuations of temperature decay very fast. Okay, so they are fast decaying temperature fluctuations. This is discussed in the paper that I'm referring to, fluctuations. Okay, so this is discarded for this type of model. There is another type of model that is the one I'm going to discuss today that are called, okay, another one is Brownian motors. Brownian motors is having a periodic potential. Brownian motors. This has been, in the years 2000, there was a lot of people working on this type of models. These are periodic potentials with an external force. So it's a tilted periodic potential, something like this, okay? This is called a Brownian motor. This is at homogeneous temperature. There is a potential, it has a tilt, so the particle is falling, okay? Sometimes the particle climbs, okay? But the net effect is to go in this direction. Okay, this was in the year 2000s, okay? There was a lot of research about this. However, the most accepted model for the motion of molecular motors is the so-called Brownian ratchets, which is the following. So you can have a net current in an isothermal environment if you have the so-called ratchet potential, Brownian ratchets, which is the following. So you have two potentials instead of one. So, for example, one is like this, and the other is, I don't know, like this. Okay, and you have a particle diffusing in this potential, but the potential is switched. There is a switching between this and this. So the particle is here, and all of a sudden, the particle takes energy and goes to this configuration. Then, because this is asymmetric, it is diffusing, but it goes to a state of lower energy like this, and then it continues diffusing and encounters a wall. So then the particle cannot jump this wall. And then at some point, this potential is also switched, and you change the other potential. And then the particle falls, and it falls down here. And then when it comes down, there's an activation due to ATP that changes the potential, okay? So this is called the Brownian ratchets. It requires, okay, this is both at temperature T. So you are at temperature T here, temperature T here, but you have a switching mechanism. And this switching mechanism is called active mechanism, or it's something that can be produced by this type of chemical reactions. This is called the Brownian ratchet, and this is the model that I will discuss briefly. Why these two potentials are introduced? It is mainly because we see these two like two configurations of the motor. So the motor can be in the filament. So for example, the motor can have the legs in the filament. This would be this state. Or the motor can be detached from the filament. So the motor has a little bit higher energy. It is a little bit detached, like this, okay? And when it's attached or detached, it can still diffuse. But it sees different potentials when it is attached, okay, attached, or detached, okay? This is the paradigm of molecular motors, and we will discuss about this in this lecture, okay? So this will be when I discuss the stochastic models, but before, let me give you a bit about mean field models, which is the first part of the lecture. And I will describe a little bit the thermodynamics of this type of motion on the average. Later, the second part of the lecture will be on this type of models, which are a very good example of stochastic models. So, okay, I will first start with this one. Okay, any question or doubt or anything?
Hello.
Hello?
Hello?
Yes, hello.
Can I ask for here the V of X is the velocity?
Sorry, no, this is a potential.
Potential, okay.
This would be a potential.
Okay.
I don't know, this was small v and this is big V.
Okay. That's it.
A potential and a diffusion coefficient or a temperature field, which is similar. This type of case would be a Langevin equation. It would be like x dot equals mobility times v prime plus noise. Okay, this will be the equation of motion for the system. There will be a white noise, thermal, and there will be a potential acting on the particle. Of course, because we will have an inhomogeneous temperature, we will need to put here a g of x. Okay. This is one type of model that is one particular example of what I explained to you in stochastic process. Okay. Here is different because here there are two types of equations when you are in this potential or when you are in this potential. And here we will have V1 of x and V2 of x. Okay. I'm writing very tiny, but later I'll give you the equations of this type of machines. Okay.
And can I ask another? The fast decaying temperature fluctuation is fluctuation in terms of time or space?
Yeah, in terms of time, this because you see that the motor is in a thermal bath, so there are a lot of molecules around. And of course, temperature can fluctuate. So there can be one molecule that gets a bit faster all of a sudden. So the motor can feel all of a sudden there are molecules that are a bit hotter in its environment. But these fluctuations are very tiny, are very short in time. So these type of fluctuations are of the order of microseconds, typically. But the jumps of the motors take, depending on the motor, but these are of the order of seconds. So these fluctuations can be neglected somehow. Okay, we will neglect, and I tell you, you don't need temperature fluctuations to explain experimental data. This is the nice thing of this. Okay, so this is almost negligible, but this temperature is, if you go with a thermometer, I tell you, here and here and here, you will get the same value. So it's something discarded for this type of modes. However, this makes more sense because when the motor is attached or detached, it's really feeling a different force. So this makes more sense for this modeling. Other questions? Okay, seems not. So let me go to this part. I'll give you simple models by now. So I first start, well, mostly I will focus in the mechanochemistry of this motion. So it will be mechanochemistry. Mechanochemistry. Why I call it mechanochemistry? Well, because the motion of the motor has there are two forces that are powering the motor. Mechanical forces, like this one, and chemical forces, like this one. So the motion, in the end, this disappeared. It brings mechanochemistry aspects of, I would say, molecular motors close to equilibrium. We will assume that we are close to equilibrium. When we use stochastic process, the nice thing is we don't assume the system is close to equilibrium. We can assume everything. We can be far from equilibrium. So now I won't use stochastic process. I will just use linear response theory. And this is what you use when you are close to equilibrium. Okay, so I'll say that we have generalized forces. So when you are close to equilibrium, you use linear response in thermodynamics, linear response. And there's a theory. This theory relates fluxes and forces. Linear response theory. The generalized forces are two here. So there are two forces. The external force, this is the mechanical force. And the chemical force, which is a chemical potential difference per fuel molecule. Okay, this is the chemical potential difference per fuel molecule. Okay, this tells you how much energy does the hydrolyzation of a single ATP molecule give you. So delta mu in reality is the chemical potential of ATP minus the chemical potential of ADP dP minus the chemical potential of P. So this means that this is equal to 0 and you are in equilibrium when ADPP is equilibrium with P, equilibrium. It means they are in the same concentration. It is positive when there is ATP in excess. Okay, in excess. There's more ATP than ADPs and Ps, so you are burning it. And it's negative when there is ADP in excess. Okay, this is okay, very basic. So now the key point is that for this type of models, the velocity of the motor, this is the mean velocity. Okay, mean velocity will be a function of, okay, this is linear response. So velocity is a flux, and these are forces. This is forces, this is a fluxes. The mean velocity will depend on the forces linearly. So it will depend in this force and also in the chemical force. The other mean velocity or mean flux is R, which is the rate of ATP consumption, will depend on the external force and also delta mu. When I'm writing this parenthesis, it means it is a force, it is a function of these two things. Okay. However, we must remark that often, okay, this is a remark. Motors often work far from equilibrium. Equilibrium, in which delta mu is of the order of 10 kVts or 14 or more. In this case, there won't be a linear relation. It won't be linear response. There will be non-linear response, and we will need to use stochastic models, okay? And it will be stochastic models. But by now, okay, this is a remark, something you have to take into account. So we are doing now a theory when ATP is bringing very little amount of energy of order kVt, okay? So we are now assuming that delta mu, this is our assumption. Assumption is that delta mu is of the order of kVt. So we can use linear response. We use linear response, it means the following. It means that we can write the fluxes as linear combinations of the forces. So we can write the following. The velocity, the mean velocity is a mobility, mu11, times the force, plus another mobility, okay, it's a coefficient, let me call it, lambda 1, 2, times the other force, delta mu. This is the chemical force, this is the mechanical force, and both together give mechanical flux. And this is a chemical flux, R. It will be mu21 F external plus mu22 delta mu. Okay, this is an assumption, this we will consider. And now it is important to understand what do different parameters mean. So first, this one here, this is the mobility. Remember, when we have F proportional to V, usually you write F equals gamma V. Gamma is the friction. So the inverse of a friction is a mobility. Okay, this is the mobility coefficient. This one here, it is like a ATP mobility. It's not that ATP has a mobility, but it's an effective mobility. It has it's a parameter that is also relating its flux with its corresponding generalized force, okay? ATP mobility. This is due to fluctuations in ATP mobility. And then there are these two parameters that I will mark now in blue, which are the mechanochemical couplings, okay? Coupling coefficients. These two are put it here, mechanochemical chemical coupling coefficients. And this should remind you, I don't know if you remember from thermodynamics in your university courses, to Onsager reciprocity relations. So if you have, usually this appears in, for example, the thermoelectric effect, that you can have a thermal gradient and this generates an electrical current, or vice versa. That in those type of systems, when you describe them with linear response, you have these coefficients and you say that the coefficients are symmetric. So there is this, there is this symmetry, mu12 equals mu21, which means that when you have a chemical force, this generates a flux. So the coupling between different forces and fluxes is the same in one direction and in the other. And this is called Onsager reciprocity. Okay, Onsager reciprocity. It's a very famous result in thermodynamics, reciprocity relation. Okay, so now something that is important is to consider. Okay, first of all, we assume that the system is stable. So this can be written also as a matrix, like V of, you can say VR is a matrix. We can call it, I don't know, matrix lambda, like this, times F delta mu. And this matrix lambda, we can say it has different elements. And the different elements are these ones. This is the first element, the second, the third, the fourth, okay? And typically, the determinant of this matrix is positive. Otherwise, the system is not stable. But we will see that this has some consequences, especially in the thermodynamics. So what we can measure is what is called the entropy production rate, sigma. It is basically the following. It will be the force times the velocity plus the rate times delta mu. Okay, this is the work done by the external force. You see force times velocity, and this is another. You can see this also as an energy consumption rate. Okay, first of all, this has units of power because it's force velocity. This has also units of power because this is 1 divided by second. This is delta mu, which is energy. So this is also a power, but this is the heat dissipated. So in reality, this is the work from the external force. And this, all this, okay? In reality, it's the power, because it's per unit time, power. And this is the heat dissipation. Heat dissipated. Heat dissipation rate, because it's per unit of time, due to ATP consumption, due to ATP. And this sigma here is the entropy production rate. So how much entropy is produced per unit of time. Okay, it is given by this in this example. So if now you take this V from this equation, so I'll put it now in green. So I take the V. This equation I plug in here, and delta, sorry, made a mess. Yeah, V, you put this, and R, you put what you have in this side, this R here, you put it. What you get when you replace, you get the following. So you get lambda, sorry, not lambda, but I have a different notation before. You get mu11 F external square plus mu12 delta mu F external plus mu21 F external delta mu, which is the same thing, delta mu, plus mu22 delta mu square. Okay, and this is like a, if you see this, this looks like a matrix multiplication because all this looks okay, I just copied sigma. It can be written as the following: a vector, which is F external delta mu, times a matrix, which is mu11, mu12, mu21, mu22, times this vector transposed, which is F external delta mu. Okay. This is entropy production. Because of the second law, this must be positive. So this implies constraints to this matrix, implies that some properties of the matrix should be in such a way that this multiplication is always positive. And what you find is that this happens when, so if and only if, mu11 is positive, okay, that's fine, this is a mobility. Also, but also mu22 is positive. And also the determinant of this matrix that I call lambda, the determinant is positive of lambda is positive. These are constraints given by the second law. The second law implies that this matrix, you cannot pick any numbers here. These numbers have to be taken in agreement with the second law. Okay, the second law constraints for these parameters. Okay. But now something that I think is very useful and interesting is to understand the efficiency of this motor, because the motor is using, so you have to think that this is a system that is using chemical energy, and this chemical energy is used to get power. Okay, so it is important to understand how efficient is this motor. So for this, we define the power. The power is W dot, we call it, which is F external times the velocity. And I also defined the heat dissipation, which in this case is given by, okay, this is the average power, just remind average power. There is also a theory which is called Stochastic Thermodynamics, where the power is the power and the work and the heat, everything is stochastic, because every motor will have a single trajectory, and for each trajectory you will have different work. And this I will explain later in the spring college. I will have a course about that. Now I just look at the averages. The heat dissipation is, in this case, Q dot. It will be just R times delta mu. Okay. So now something that is important is the signs. Remember, in thermodynamics, when the work is positive, it means we are doing work on the system. When the work is negative, it's the system is doing work on us. So you extract energy. So when you have this, F external times V, which is W dot, when this is negative, is that the motors perform work. So you can extract work like from an engine, in this case from a motor. When R delta mu is positive, this is the interesting regime, we have ATP hydrolysis. ATP hydrolysis. So this is the region which is of interest for us. We would like that work is negative and the heat to be positive. This is the region of interest for us. Okay. We would like to understand this process of ATP burning that gives work, right? Of course, if we had, for example, R delta mu, if it would be negative, we will have ATP synthesis. It will be the opposite. And there are motors that work like this, that synthesize ATP. For example, there's a motor involved in photosynthesis. For example, it's called F1 ATPase. You can check about it. It's a very interesting biological system that produces ATP. But it has another fuel, which is a fuel of protons. We are not talking about this. We are talking about other type of motors like kinesin, myosin, kinesin, myosin, dynein. All these motors use ATP to move. Dynein, they burn ATP to move, to extract work. Okay. This is another type of motor. We could talk about them, but maybe later in the course. Okay. So this is the regime that we are interested. And now what is very important is that in here, we can plot a phase diagram. So people doing research in motors were interested in phase diagrams. So it means that the motor can have different phenomenologies. The phase diagram will be in this plot. It will be external force, and this will be chemical potential. And here what we will define is an efficiency. I said I'd like to understand this is called efficiency of the engine, which will be defined as minus the power divided by the heat dissipated. Okay. So somehow this is giving you an idea of I'm getting an energy input, which is Q dot. This comes from the fuel, from the ATP, and part of it I'm using as work in the system. Okay, the rest I'm using to change the configuration of the engine or the machine and so on. This is my definition of efficiency in this case, and minus W dot will be minus Fx external force times the velocity, and the heat will be R delta. Okay, and now we will look in this diagram what happens with this efficiency. So first of all, okay, it's all clear up to now. If you don't understand, please ask.
I have a question.
Yes.
When you say the motor perform work, that means the motor will back forward.
Performing work means that in this context, it means that F times velocity is negative. It means if F is negative, V, okay, must be positive. Okay, so if we look at the figure we draw here, in this case, the force is negative. So there is a cargo in the backpack of the motors. The motor has a force that is pushing him behind, but still the motor is moving forward. This is what doing work means here. This is what negative work means in this context. So there is a load, but the motor can work against the load.
Okay, I see. Now, what is the impact of the flux of ATP?
The impact of the flux is that the flux has an impact on the net velocity because there is this, in this theory, there is a coupling. So delta mu, when delta mu is very large, it means the fuel is giving a lot of energy. This is increasing the velocity of the motor with this coefficient. Okay.
Okay.
So the more energetic is the molecule that you burn, the faster you will go.
And,
okay.
Okay. What is the condition to back forward?
Sorry?
The condition to back forward, because here we said if the delta mu is high,
yes,
we move forward.
Yeah, sure. But it depends on this equation. So if you want to go forward, this should be positive. Okay?
Okay.
So it means if you want to move forward, okay, let me just do it in the next page. So if you want to move, okay, move forward, you need the following. So you have mu 11 v plus mu 12 delta mu. This was the net velocity. Sorry, I did a mistake here. This is the force. Okay, this should be the force. Move forward means this should be positive, right?
Okay.
Okay, so then this means that delta mu should be greater than minus F external times the ratio of these coefficients, mu 11 divided by mu 12. You need this condition in order to have motion in the positive direction. So, for example, if these coefficients are the same, so if you have mu11 equals to mu12, this is not a typical case, but it can be, and the external force is, I don't know, 2 piconewtons. Okay, these ones have units, so there will be something here, okay? This will be, for instance, okay, sorry. The coefficients have units, so you cannot write it like this. I can write, for example, mu11 divided by mu12 could be, let's say, 8 nanometers, for example. This one will have units of nanometers because this is energy. So this is piconewtons, the force. So the rays of the coefficients will have units of length. Force times length is energy. So this means, for this example, that delta mu should be greater. Okay, the external force is negative because you are pushing backwards. Okay, you have the motor and the external force is like this, minus 2 piconewtons. Okay, so this with a minus times minus plus 2 times 8, 16 piconewtons nanometer, which is 4 kVts. In this case, it means if my molecule gives me 4 kVts of energy, I move forward. If not, I move backwards.
Okay.
Okay.
Yeah.
So this is why these equations are useful. So you have to read this again, but this is the net velocity in V, and this is the net velocity in ATP. So if R is positive, you are burning ATP. Right? You can also have a strong external force such that you produce ATP instead of burn ATP. This is what, okay, it will appear now. Don't worry.
Okay, thank you.
Welcome. Other questions related to this?
No.
Very good. All right. So this motivates this question, which is what is the efficiency along this plane? You following Boris' question, you see that in different points in this diagram, we will have positive or negative velocity. So you have F and delta mu for a given values of this. If you are here, you can have positive or negative velocity. It will depend. Let's see what is the value of this efficiency. So first of all, if there is no force, Fx is 0, so we are in this line. Actually, in all this line, the efficiency is 0 along this line. In this line, we have 0 efficiency, eta equal to 0, 0 force, because the external force is 0, no efficiency. On the other side, there is also the line of 0 velocity, which is also 0 efficiency. This is the line that I was discussing now with Boris, because if you put here a 0, then there is a line of parameters in which the system has 0 efficiency. It is when this is equal. Okay? When you have here equal, an equality, you have 0 efficiency. In this case, you see that force and delta mu are related like a line. This is like y equals to x times m, okay, with a minus. This is a line. Delta mu versus F is a line. So there is a line here in which also we have 0 efficiency. Here, there is also eta equals to 0. Because along this line, there is 0 velocity. Along this line, okay? So this is the line, we can write it like as follows. Is delta mu is minus mu11. This is delta mu is minus mu11 divided by mu12 fx, this line. So in this line of parameters, of force, sorry, not parameters, of force and delta mu, 0 efficiency. Here there's 0 efficiency. And then we must see something that if we are here, F is positive, delta mu is positive, R is positive, and B is positive. So the efficiency is negative. So we are not interested in this area. This is not interesting for us. The only interesting region for us is here and here. In these regions, eta, the efficiency is positive. Here is 0 along this line. It is 0 along this line. And then, more or less in the middle, there is the maximum efficiency. So you can prove, this is a bit of simple algebra, there is here a line of maximum efficiency. There is here the maximum efficiency, which is a very important parameter for us. So you like the motor is as efficient as possible. You can prove, this is some algebra, I will skip this because it's very mechanical to prove. The eta is smaller or equal than a maximum value, which is the following. It is, you can prove that is 1 minus square root of 1 minus sigma squared divided by sigma. You can prove this is the maximum efficiency, and sigma depends on the parameters, which are these ones. These are the parameters of the model. It is mu12 squared divided by mu11 mu22. Okay, this is a number. When you have this number, this gives, with this formula, this gives you the maximum efficiency of the motor. All right, you can prove this after 2 or 3 steps in this. Okay, so just to wrap up this part, let me just have a short discussion. It is the following, that at the stall force, remember what was stall force? Stall force is when the motor doesn't move, V equals to 0. The efficiency vanishes, okay? Efficiency equals to 0. And this is an important difference with heat engines. Difference with heat engines. For example, the Carnot engine. Example, the Carnot engine. Carnot engines. Because this type of engines maximize efficiency, which maximize efficiency in the quasi-static limit. Okay. Maximize efficiency in the quasi-static limit. It means when you have a Carnot cycle is you have a cylinder, which this is the volume, this is at hot temperature, you expand it, the hot temperature, TH, then you cool it down at the same volume. Okay, actually this is the Stirling engine, but it's similar to Carnot. This is cold, and then you compress it when it's cold. We can talk a lot about engines. This is one of my favorite topics in physics. In this type of engines, when you do a cycle, you take some time to take an entire cycle. The maximum efficiency is obtained when you drive the cycle infinitely slow. That's when you reach Carnot efficiency. This is when you go to the quasi-static limit, you have the maximum efficiency, which is the Carnot efficiency, 1 minus Tc over Th. Okay, this is the maximum efficiency. However, molecular motors are different. When you go very slow, you are not efficient. You have 0 efficiency. So this is a totally different machine in reality. It means molecular motors are not Carnot cycles, are not heat engines, are different, are something different. Okay. It's one point about the discussion. And another point about the discussion is that I'm only discussing averages, but if I think about a single motor moving, the motion, okay, motion of a single molecular motor, this will be, I could represent the motion in a 2D plot like this, okay, in which this will be the position in the filament, and this will be the number of ATPs that I consume. So if I consume an ATP and I move 1 unit, I will move in this diagram like this, okay? I move forward and I consume 1 ATP. But I could also move forward and not consume 1 ATP. So I could go also like this, okay? And I could also consume ATP and not move. So I could do like this. So this will be a random walk in the space of, this will be position of the motor. And this will be net number of ATP consumed. So if a single molecular motor will have this type of motion, which in the diagram, energetics diagram that I discussed here, which, okay, this was like the power and this was the heat. Well, this is not the power, but the work, and this is the heat dissipated. In this diagram, it becomes a stochastic trajectory. So if I plot here W and here Q, and I said these were the lines of zero efficiency, it means that one of these trajectories will be a trajectory moving here. Okay, something like this. One case, another case, and so on. So each of these trajectories will have a mirror in this diagram. This means that here we have stochastic dynamics. So for a single motor has stochastic motion, but this, because the motor is in contact with a work, with a force, and with a heat bath, this will bring for each of these a mirror trajectory that will have stochastic, also thermodynamics. So for a single trajectory of a motor, we will have a single trajectory in the heat work space. It will be stochastic thermodynamics. And this is the motivation of, this is the field in which I work. I work in stochastic thermodynamics. So it's a very, okay, this is a sketch, a very dirty sketch of what we do, but this is the motivation, where it comes from. So a single motor is small, it has fluctuations, and because of these fluctuations, they also bring fluctuations in the heat. So the number of heat dissipated to a thermal bath is stochastic, and also the work done is stochastic at the level of, very important, single motors. Here, what we did was the average for, it's an ensemble of motors. You have one motor moving, you have another one is here, you have another one that is here. You take the average of them, and this is what we are doing here. Okay, just it's a remark. Right. I should stop at this point, and then I will briefly introduce these ratchet models. Any question or doubt? Okay. Then let me stop 5 minutes, and then I will do the last half an hour of the class in, okay, after the break, right? Okay, I take it as a yes. So I briefly stop the recording, and I share the whiteboard with you. So we were discussing a little bit about linear response models, which were about the net velocity, net fluxes in motors. But now I'll give you a popular model, stochastic model of molecular motors, which is sketched as follows. This will be stochastic model of motion for molecular motors, which we could think about it as a flushing ratchet model. This is a way this is usually called, flushing ratchet. Okay, so the sketch of the model is as follows. So we have monomers like this, and we have the motor sitting on a polymer. Example, this could be kinesin. Like this. These are the legs of the motor. is in an attached configuration. This motor moves in 1D, so this would be the x-axis, and the motor can switch on and off its, or it can change its state as follows. So this is the polymer, and it can go to a detached configuration like this. So it can detach. This is like now detached from the polymer, from the track. This is the detached state. And of course, there are fluctuations in the motion of the motor. So this is fluctuating. There are fluctuations, both in the attached and on the detached state. As a result of this switching, the motor will have a net motion in one direction, which will be, for example, here. Okay. So what we will say is that each of the different states is encoded as a diffusion in a periodic dependent potential. Okay, sorry, in a position dependent potential that is periodic and asymmetric. So there are two states, and in each of the states there is two states that switch stochastically. Each of these states is characterized by a position-dependent potential. Dependent potential, which will be V1 or 2 of x. So there are two potentials, V1x and V2x, and they are periodic and asymmetric. Periodic, so there is V1x plus minus L equals V of x. So the period is L, V1 of x, and the same for V2, okay? This is V2x plus minus L equals V2 of x. Okay, here you could have NL, and N is 1, 2, 3, and so on. So this, we assume that the filament is infinite. And the motion is modeled as a one-dimensional diffusion into switching potential. Okay, so the motion is a one-dimensional diffusion into switching potentials. Switching potentials. Something else that I would like to say is that the switching rate will depend on what is the motor. So now let me give you a more clear idea of what I'm talking about. So we will have the following. So we will have a potential. Okay. This will be the potential. This will be x. And here we'll have, this will be V of x. Potential will be the free energy of the motor. And x here will be the position of the center of mass of the motor. Okay, the position of its center of mass. We say that there are two potentials and there are switches between the potentials. The potentials, I will try to draw them the best I can. So let me see if this one is okay. Okay, this is a bit, this is fine. So the potentials will do like this. Okay, this is one potential. Okay, maybe it's a bit exaggerated. And the other one, it's as follows. Okay, I'm not very happy with this drawing, so let me do it a bit like this. So this will be one potential, like this, periodic. Okay, and the other one, so this one has the minima here, 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 and the other one, so this is periodic, you see it. The other one is also periodic, but the period, so the period length will be the same. So this distance here will be L. The other one will have also period L, but the minima of the potential are located in general in different positions. So now the minima will be here. We will do like this, and then like this, and the minima will be, for example, here. Okay, like this, and the minima is here. Okay, so now you see that the minima is located here, okay, in a different position than this one. I'll take as a reference point, this will be 0. And now something that is extremely important. Okay, first of all, I didn't define what are these things. This is V1 of X, potential 1, and the other is V2 of X, the second potential. This will be attached, and this is detached. So the motor can be attached, and suddenly, boom, it gets detached from any position. So, for example, from here, it takes energy, and it gets detached. Okay, and we say this happens at a rate omega 1 of X. Okay, this is the switching rate from state 1 to state 2 and from position X. And we also have the opposite. So we have also this rate going backwards. Okay, this will be omega 2 of X. Okay. So do you follow me on this, or is it too complicated? Is it too easy? Please let me know, because it is very important that you understand this picture.
Hello.
Yes.
Sorry. Here, omega 1 and omega 2 are not equal.
In general, not. In general, not. Okay. Omega 1, so let me just say it, omega 1 of X is the switching rate from 1 to 2 at position X. And omega 2 of X will be from 2 to 1 at position X. Okay? This is the idea. Do you all follow me? More or less? Okay.
I have a question.
Yes.
What is the meaning of the minimal potential? Because here is like, we can consider as a sinusoidal.
Be careful. It cannot be a sinusoidal. It cannot be. In these ratchet models, the potential is, okay, periodic, but I forgot one thing in this potential, that is asymmetric. Okay? The potential is asymmetric. It means if you flip it left to right, it will be something like this. First slow and then fast. First slow and then fast. Okay? This is asymmetric potential. This is after flipping. Okay? The sign is periodic. If I do this is the sign, I flip it, it is the same. Okay? This is asymmetric. It's like if I do something like this. This is asymmetric. Okay? It is not like a sign, it's asymmetric. And this is essential to get transport, because if you see, let's say, for example, you are here, the particle is moving here, the particle is the motor, and then you switch on, you come to a place where there is an asymmetric potential. So the particle will most likely go in this direction. You see? And this will generate motion. The particle falls here, then jumps down. Okay, the jumps are stochastic, but most of the times you will be here because of the diffusion, you go to low energy state. Then you come, you find this wall, this slope. So you are sliding in the slope, then you will come here. Then you will switch on. You could switch off. When you switch on, at some point, it will slide, okay? And this combination of slides will generate motion in this direction. Okay, so it's very, very, very important that the potentials are asymmetric.
Okay, since at each position X, we can switch. And if we consider the minimal position for the potential, what is the meaning for the motor?
The minimal position is somehow the equilibrium position, because the polymer won't be homogeneous. It won't be just a flat line. The polymer will have a structure. So you can think about this like the structure of the polymer. There is one place in which the motor is feeling better because of the structure. So I don't know, I can do a very bad drawing, but maybe this is, if you zoom in, then this has a structure. So it is something like this, maybe, no? This is one monomer, for example. This monomer, I write it like this. And then maybe it's better because of the structure, the motor puts the leg here, okay? And then here is the other, and the other leg will come like here. So this minimum is when the motor is in this configuration in which it's feeling the structure is really stable in this case, okay?
Okay,
so,
that means at that position, the motor cannot move forward or back forward, or he will try to stay at that position.
It will try to stay at that position. So it has to, in order to jump to the next step, it has to overcome a barrier. You see, no? There's a barrier here. But it is better for the motor to detach and then jump the barrier this way. That's why you need this rate here. You see?
Yeah.
That's the idea. It's like you are running against a wall. And of course, you could have a lot of energy and jump. So you could come with a lot of inertia and jump this way. You could. There is some probability. But there is a big wall here. So it's better to detach and then use a fluctuation to jump. This is what happens here. You detach, and now you are fluctuating, and there is a fluctuation that can bring you here. And then you will float and then attach, which is boom, this one. Okay?
Yeah. And if the fluctuation is due to the ATP.
Yes, that's the important thing. Here there are thermal fluctuations, which is what happens here in the potential and here in the potential. But there are then these omegas that are due to ATP. So these rates are triggered by ATP. So ATP comes here, ATP binds, you hydrolyze ATP and gives you high energy to jump. This is done by ATP, this one, okay? Okay, but you could also jump because of a thermal fluctuation. It could come a lot of water molecules at some point, push you and get out like this. So we will do a model that will have the two options. There will be two channels in omega-1. You can come with a thermal fluctuation, but with ATP. But it will be essential ATP here. You will see. Without ATP, we won't have a current. This is the main result, okay?
Okay, thank you.
We will see this later, okay. Fine, so this is the motivation. And okay, if I want to give you some numbers, because I'm just giving you a sketch. So for instance, if you think about Myosin Motor, we will have a potential that will be like this. In the Myosin Motor, it is important that the distance between the minimum and the maximum is around 3 nanometers. But the distance between, so the period is around 10 nanometers, just to give you an idea of what is the length here. So there are asymmetric barriers. This is the main point, asymmetric barriers. Okay, fine. So given this, let me at least give you the equations for this type of dynamics. We will use things we know. we will use Fokker-Planck equations to describe this. So we can use what we learned to describe this type of molecular motors. Okay, so there we go. So we will describe the dynamics of, okay, we have this potential, this is V1 of X, and then we have V2 of X, and this will be, okay, one of the minima, sorry, this minima will be 0, to be X, and I repeat, we have the rates omega 1x and omega 2 of X, okay? So now, what we do is, this will be the Fokker-Planck description. Planck. So we will use probability densities. So we will define Pi as Pi xt. Okay, I want to write the xt's below, but it means if I write this, it means it has x and t's inside. This will be the probability for a motor to be at time t in potential I. Of course, I is equal to 1 or 2, and position x. Position x. Okay. In reality, one should do a Fokker-Planck with two variables, x and I, but I'm going to simplify it in a way. I'm going to write it in a way the two states appear and they are connected to each other. This is similar to the model of microtubules that I explained you in the last lecture. Okay, there were two states, growing and shrinking, and we had different speeds in each of the cases. Here it's more involved, you will see, but it's the same philosophy. So we will have Fokker-Planck equations with sources and sinks. Okay, there will be sources and sinks, which will be these transitions. If I have only one potential, there won't be source and sinks. There won't be probabilities sources anyway. It will be just a typical Fokker-Planck. Now we have sources and sinks. We have two states. So we can write it like this: partial t of P1. Remember, P1 is P1 xt plus partial x j1 equals partial t P2 plus partial x j2 equals, okay, this is the current I usually put. Usually I write the Fokker-Planck like this: partial t of P is minus partial x of j. This is the way we were writing the equations. But now we have exchanges. So we have P1, we have P2. Sorry, I'm doing a bit of a mess, but just to let you know. So there are the currents, partial xj2, and then there are exchange terms. So there will be, we are losing from 1 with rate omega 1, and we win from 2 with rate omega 2. Okay, so I'm writing it like this. Okay, P1 minus omega 2 P2. Okay, but these J's will have the structure of a Fokker-Planck. You will have a drift and a diffusion in each of the potentials. That's what I'm going to write now. Okay, so maybe it will be more clear once I write it a bit slower. So it will be like this. And now I'll write here minus omega 1x P1 plus omega 2x P2, and here omega 1x P1 minus omega 2x P2. Okay, so this is the way we describe the model. There are two probabilities. They have currents inside. I will write now the currents, and then there are switches. So from 1 we lose with rate omega 1, and we win with rate omega 2 with probability P2, and the opposite for state 2. Now what is important is, what are these currents? So the currents, okay, this is the Fokker-Planck equations. Fokker-Planck equations. the currents. So I haven't finished to write the equations because I need to write what is this. So J1 in reality is, in reality, you remember the current was basically, you remember how to do when we had dx was f dt plus gdv. Now we have something similar. In each of the potential, we have one of these equations. So the Fokker Planck was partial T of P equals minus partial x of j, and j was, okay, I forget something. Here there is a mu mobility, it's mobility force here. So this was mu, if I remember well, mu f p minus 1/2 g squared partial x of p. Okay, this is what we knew from our stochastic process course. Okay, right? You remember this, right? So now it's similar, but we just have to be careful with how do we deal with the constants. But it is very simple. Here we can just write it. Well, actually, I can write it for both. And you can just follow in the paper as well. So Ji, and here I equals 1 and 2. Ji will be the following. Will be mu I, this is the mobility in state I, and then we will have minus kBt. I'm writing it in a different order, but you will see it makes sense. Partial x of pi minus pi partial x of pi plus pi f external. Okay. So what does this mean? So you see that here there are three terms. We can also write, for example, J1 is, the first term is, okay, we can take this with this with this. This is basically mu1. And now we have minus partial x v1. So this is a force due to the potential in 1 plus, sorry, there's a mistake here. There is a mistake, minus, okay, plus f external. So we are saying there is an external force. The model has also an external force pointing in x. Okay, this is all this times pi. So this is the drift term, like I showed in the previous lectures. So this means in the Langevin equation, there are two forces, the force from the potential and the external force in x. And then there is this minus mu kBt, which in reality, mu kBt is the diffusion coefficient. Okay, this is d. Remember, this was 2d. So I have minus d. So this is d1 mu kBt times partial x of p1. This is p1. Okay, p1. So this is the typical Fokker-Planck current inside this potential, and J2 is the same inside this potential. So now we have Fokker-Planck current here and here due to diffusion. It has potentials, it has external forces, so it's a very rich model, this one. And then we have the switches, right? So this, you can write it also as a Langevin. Okay. Why this is important, and this is the way I will finish today the lecture, is I'm not going to show the full solution of the model, but I will tell you that there is an effective 1D motion. You can write this as an effective 1D diffusion, in which in the stationary limit, we will have the following. The current will be the current 1x plus the current 2 of x. This is the total current of motors. And we will say that the probability to be in state x, the probability that I'm here, as the probability that I'm here in this state, plus the probability to be here in the other state. This will be P1 of x plus P2 of x, okay? This motivates me to define these coefficients. Lambda 1 will be the fraction of times I'm in state 1 divided by px, and lambda 2 of x will be the fraction of time I'm in state 2, okay, divided by px. So you see that this plus this equals 1, because p1 plus p2 is p, okay? So we see that lambda 1x plus lambda 2x equals 1. This is an important point. Okay, so there is a lot of algebra. This model is very difficult to solve, but one can solve, one can get this value, the J. We can write an expression for the net current in the x direction, J. And it is the following. The net current, so this is after some algebra, the net current is the following. Is an effective mobility times minus kVt partial x of p. Now the p is the sum of the two p's, minus the total p partial x of an effective potential, okay, this depends on x, plus the total p external force. So this is like a 1D diffusion with this mobility, this effective potential, and that's it. So there is like an effective potential describing this. Just let me just give you the result so you can take a look. This effective mobility, okay, effective mobility is the following: mu f. This is x is the mobility in the first potential times lambda 1 plus the mobility in the second potential times lambda 2. Okay, this is simple to understand. What is even more important is the effective potential. What is the effective potential in this mode? It is very non-trivial, the equation, but you can convince yourself if you check the math. Vfx. So this, what I'm showing you, you could do it if you check the equations. You can go on and check it. It's a bit. It's not one step, but if you do the math carefully, you will find this. Okay, this is the integral in 0 and x of dy, and now we have in the denominator. Actually, we have mu1 lambda 1. Actually, we have in the denominator mu f plus mu2 lambda 2. And then here we have mu1 lambda 1 partial x v1 p1 plus mu2 lambda 2 partial x v2. Okay, so this is this part here is we are weighting the two potentials, this one and this one. This one here is the effective mobility of x. And then there is an extra term that is not so important, that is kVt logarithm of mu effective x divided by mu effective c. Okay, so this potential looks a bit horrible if you look at the formula. It is not very trivial to understand it, but what you should realize is that in general, we'll say, in general, lambda 1 x and lambda 2x, in general, these two have the symmetry of the potential of v1x. So if these are periodic, also these lambdas are periodic, v2 of x. What is very important is that, okay, if these two are the same, the potentials are the same, you will have this sum and this will become partial x of v. So here you will have a periodic potential. But in general, this potential is not periodic. So what is important from this equation is that in general, Bf of x, the effective potential, is not periodic. Very important, this is not periodic. So there is a slope. If you calculate VFL minus VF0, this is not zero in general. It is not periodic. So we have periodic potentials, V1 and V2, but like this. But the effective potential, this one, in reality, it is tilted. So from these two and switches, we have an effective dynamics that is only one potential, no switches, but the potential is tilted. It's doing something like this. This is V effective X. So this switching gives us, okay, this current that you see, it has diffusion, it has external force, but even if this is zero, even if there is no external force in the motor, this potential is in generally tilted. So the particle will move in this direction. It is very, very important. And the key part, and I will finish with this today, is that when is this non-periodic? So, okay, so let me just say this. It's not periodic even when not periodic, so it is tilted, even when the external force is zero. This is remarkable. Okay, so the question now is, and I finish with this, when is the effective X periodic? This is not simple from the formulas. It's not easy to see from the formulas, but I can tell you the answer. V periodic means it's the same as saying no current. It means that no energy is supplied. So we have the following: if no chemical energy, there's no ATP, is supplied. We have the following: omega 1x equals omega 2x times the following: E of V1 of x minus V2 of x divided by kVt. This is called detail balance condition, okay? Detail balance. So if you have this condition, what you get is that lambda 1 of x equals 1 divided by 1 plus E beta B1 minus B2, x minus B2 of x. So this is like the two-state model. If you remember a two-state model, one of the probability of one of the states was 1 divided by 1 plus E to the beta E. And the other was lambda 2 was E beta V1x minus V2x divided by 1 plus E beta minus V2x. So this is the two-state model. This is the equilibrium. When you have this, V of x is periodic. Periodic. You can check. You can check actually with this formula. If you have this condition, this will be periodic. And then there's no current. This is called the detail balance condition. And it's a very particular condition of the rates. So if you have this, so if the rates, if these two rates are related up and down in the same position, are related with the values of the potentials, this here and this here, there won't be current. Because this will be like a thermal excitation of the system. Okay? So when you have detail balance, no current. But when you break this condition, there will be current. This comes to the question of bodies. So you need chemistry. You need chemistry. If whenever, okay, actually, whenever, any time that omega-1x is different to omega-2x E V1x minus V2x, KBT, there will be currents. So Vx effective potential is not periodic, and there will be currents. And this can be done with ATP. I don't have so much time today, but in the next lecture, I'll show you in a model how ATP enters here. So this is the most possible thing. I mean, this is a very precise condition, but in general, you won't have it fulfilled. You will have, they are different. They are different. In this case, you will have current. So just one example, I give it here. I think Dionesa was saying about what if they are the same? So what if omega-1x equals to R, for example, and omega-2x equals to R? I make this question, no? So I have the two potentials. One is like this, the other is like this, so on. And now I switch with rate R and with rate R. Okay, what does it happen now? What do you think? Is there a current or there is no current? Any guess?
Is there no current?
No current, but you see, omega-1x is R, omega-2x is R, but then if you jump from here, the potentials are different. So this condition is not satisfied. Okay? So detailed balance is broken like this. So there is a current. So you have symmetric switch, but this generates a current in the system. That's the main point. Okay, let me just, maybe this is a bit not obvious, but so this is the case where there is no current. So the rate omega-1x divided by omega-2x should be e to the delta Bx with beta, no? So here, let's say this is potential 0, and this is potential, I don't know, let's say V or E, for example, no? So imagine I jump from here to here. The potential here is 0. The potential here is E. So if I want to have detailed balance, so no current, which is this, the rate up and down should be related by e to the minus beta E. Okay? So at this point, let me call this x star. At x star, the ratio between this jump and this jump should be e to the beta E. Okay? But now, if I put R and R, this is R divided by R is 1, it's not e to the beta E. So this won't happen, okay? So equal switching rates up and down break this condition, detailed balance. And then you will have a current. So the idea you had in the beginning, equal switching rates, is very nice. Because with these potentials, you will have a current, just switching randomly at the same rate. Okay, you see my point, at least knowing these formulas?
Yeah. Can you repeat the part? Like what causes omega?
Sorry?
Or I mean, what causes the switching?
Okay. This was the next part of the lecture. So,
Okay.
but I think I should say it because if not, okay, it's just 5 minutes more. So I give you just one case, which is the case of ATP hydrolysis. So this is one model of ATP hydrolysis. maybe we finish the course today, which is it breaks detail balance. It has broken detail balance. Okay, so ATP can make these switches. Okay, and the way we can model it is as follows. We can have that the model is as follows. ATP hydrolysis triggers 1 to 2. Okay, so when we are in the bottom potential, when we are attached, we use ATP to be detached. Okay, but in the detachment, we are not using ATP. This is a very, it makes sense, this type of one. So the way this is modeled is as follows. You take as this rate, up detachment rate, you write it like this. Alpha x e to the mu ATP divided by kBt plus omega x. And then you put the potential, E V1x kBt. This is one way of doing it. There are many ways. So this part, is in this channel, there can be two possibilities. You can do this transition due to chemical reaction, which is this. So that's why this is appearing. When you have a lot of ATPs, you will jump this much faster. Or you can do this channel as well due to thermal fluctuations. Okay, there's a thermal fluctuation that detaches the motor. Fluctuation. Okay, this is omega 1. Omega 2, we take it similarly, like at this, alpha x, E, and now we put the reverse reaction. So this one, ATP plus mu P divided by kBt plus omega x times E V2x divided by kBt. Okay, so now, again, this is from the chemical reaction, this is from thermal fluctuation. Let me just try to be brief. We can quantify omega, which will be the difference between omega 1 and omega 2 times E V1x minus V2x over kBt. Okay, this quantity is 0 if you have detail balance. Just if you go back, when there's detail balance, omega 1 and omega 2 are related with this. So if I do omega 1 minus omega 2 with the potential, this will be 0 if there is detail balance, and non-zero if there is non-detail balance. Okay, there's non-detail balance. I don't know why there's some sound in room H, but please, you can take it out, it's better. Do you have a class now?
Yes, at 5 o'clock.
At 5, not at 4.
No.
Okay. Give me a second because there is a problem with roommates, so I will just save here. Please shut the sound of room 8. Okay, I try to do the best of this. So I continue. I just finished with this. So this measures how far we are from detail balance. And in this model, this omega x is as follows. So you get basically alpha x, then E V1x plus mu ATP. Okay, this is in the paper I gave you. You can check it there as well. Times 1 minus E minus delta mu divided by kBt. So this is nice because with this choice of rates, you see that the deviation from detail balance, so this parameter, sorry, I didn't do well. this parameter that I'm showing here. It has a prefactor. This is positive always. And there is this term here that is crucially depending on the chemical reaction. When you have delta mu 0, this is 0 and there is no current. And when you have delta mu different to 0, this is non-zero, you break the intervalence and there is a current. So you can simply get a current by adding the chemical reaction that is acting differently in different x, but it's fueling with the same chemical reaction everywhere. So everywhere you have ATP that can come and put the system up. So simple models with ATP can lead you to a current here. So it's one of the, what we say in general in molecular motors is you can detach the motor with a thermal fluctuation, so I say here with thermal fluctuation, or with a chemical reaction. This is the most general thing. You have this, you can have a current, and you don't need an external force. But this is a very important take-home message for today. So it comes here. You don't need an external force to get a current. Okay, it's non-periodic, there is a current. Molecular motor does not need an external force to get a current. You can have an effective tilted diffusion by switching potentials and breaking the intervalence. That's the thing. What you need to get a current, okay, and this is the conclusion. Current in motors needs two ingredients. One, switching potentials, switching asymmetric potentials, ratchets, potential, but not all the switches give you current. The second ingredient is break detailed balance, e.g. with ATP or chemical reactions, they break the intervalence. Okay, this is a very important take-home message from today. I'm trying to find this thing. Okay, very important. And I think I'm done with this, unless you have questions. Any questions? This has been a very intense class, but so I recommend you to check the recording. But if you have any questions here.
I want to ask, so for molecular motors, the current is measurable?
Yes, because you can go to, you can do an experiment and look in the microscope. Okay, you're in the microscope and you have an image and there are these micro tools, like you have tracks, and you can put fluorescence in the motors. This actually will be in another class, but you make good questions. So the motor is here and it's moving. You can do data analysis of movies and look at motors moving in tracks. Each of them is stochastic, but you can collect the data and there will be one like this, another like this, one like this. And if you do the mean velocity, that's the current. This is T and this is X, okay? So one can measure the current in experiments. And there are a lot of, I mean, this is measurable since the year 2008 or 2005. People is already measuring this in the lab. Yes. So one can measure this. It's not easy to measure the ATP current. This is still an open problem. People cannot see in a single motor how many ATPs is consuming. We don't have resolution to see this. But we have resolution to measure, for example, you can see DNA polymerase moving in steps of 3 angstroms. This, I can send you a paper later. It's really impressive. Even these steps, you can see steps like this of 3 angstroms right now. It's really, really incredible. Really incredible. So one can measure this here. Also fluctuations. Other questions? No questions? Okay, so we then finish by for this year, 2020. I'll do, I think, 2-3 lectures more in 2021. I was teaching almost everything I wanted. So even I could end the course here because we did a lot. I'll give you the homework for the stochastic process at the end of the week. There will be a generous deadline, and that's it. I end wishing you Merry Christmas. So I just write it here. To all of you, I hope you have a good time in this break, and we keep in touch and we talk soon. Okay.
Thank you. Merry Christmas to you too.
Bye. Thank you.
Thank you.